Numerous tests of the controlled electron capture reaction hypothesis have yielded positive results. This includes a completely independent first principles test by Tom Claytor before he retired from Los Alamos National Lab. After Tom retired from LANL, he ran another 11 tests of the hypothesis. All of those tests reliably generated consistent nuclear effects in the generation of tritium. The CECR hypothesis also explains experimental results throughout the field. All LENR, CANR, CF effects can be explained with the electron capture reaction hypothesis. Many different disciplines use the same equations with different variable names to explain similar phenomena. Therefore, those fields that I drew on to build the ECR hypothesis are not an exclusive list, just the ones I was originally drawing on. In the remainder of this presentation, I will show how and why ECR provides an explanation of the experimental results researchers in this field have observed. It will also show why Brillouin Energy's controlled electron capture reaction model allows us to control the process. Since 2005, several prototype reactors have been built to test the hypothesis. Repeatedly, these reactors have produced positive results. This pressurized reactor, run at approximately 100 bar, produced roughly 175 watts of reaction energy. The output was measured using the flow of Mobile-Therm 603 heat transfer fluid. That is 2.1 times more thermal energy out than electrical energy in, and begins to validate the operation in a pressure vessel, should allow the scaling of Brillouin Energy's wet technology to commercially useful levels. Tritium formation is a step in the reaction cycle. In reactors designed to produce heat, it is possible with some difficulty to disrupt the cycle and deposit some tritium in the electrolyte. In September 2014, we sent 5 electrolyte samples to Tom Claytor, 1 blank and 4 that had been run with the intent of producing tritium. As you can see, we were able to reliably produce tritium in all 4 samples using 3 different types of reactor. Tom also reliably produced tritium in his first principles test of the Brillouin energy hypothesis. Here we have electron shell energy level diagrams. The electronic configuration of nickel is shown on the left and palladium on the right. Nickel is the first and lightest element in the platinum group, and palladium is the second platinum group element. The various shaded blocks represent the first through the 5th electron orbital shells in the standard model of the elements. The SPD nomenclature is repeated because the shapes of the orbitals are similar across shells. These shapes are significant to the mechanism of the electron capture reactions. S electrons tend to have a spherical shaped orbit. The p orbitals tend to be teardropped in shape. The d orbitals have a combination of toroidally shaped and a sort of a cross between mushroom cap and kidney bean shape. The height of the boxes corresponds to the energy level of the electrons in those orbitals. Yes, the s sub n plus 1 orbitals are actually lower in energy than the d sub n orbitals. These diagrams typically show the ground state of elements. As energy is added to nickel, the electrons in the s4 orbitals will jump up and fill the last 2 available orbitals in the d3 shell. If you look at the elements that seem to support the Fleischmann-Pons or excess heat effect, they have the following shell similarities in common. They have full or nearly full d sub n shell, and an empty or at least room in the s sub n plus 1 shell. Palladium is the only element in the periodic table with a full d sub n shell, d4, and an empty s sub n plus 1 or s5 shell in the ground state. I believe that this s sub n plus 1 orbital energy well represents the trapping points that hydrogen occupies in the materials that work. One of the material science ahas that set the ECR hypothesis in motion is the fact that hydrogen will pass through palladium, but helium will not. As atoms go, helium is about 1/2 the size of hydrogen, yet it will not pass through palladium, and hydrogen will. This indicated to me that hydrogen must enter as an ion. Indeed, it has been shown that hydrogen actually enters with a fractional charge, or less than 1 electron per hydrogen nuclei that enters the lattice. One way to visualize the transport of hydrogen through palladium is as an external gear pump type mechanism. The teardrop-shaped p orbitals act like the teeth of an external gear pump shown in this animation. The d orbitals in combination with the lattice nuclei act as the casing, shown in blue. There is only room for a single hydrogen nuclei, shown as green, in between each p orbital tooth and the casing. Hydrogen nuclei can easily tunnel to an adjacent lattice site, seen as the green hydrogen nuclei moving through the system. The electron shell structure of palladium provides this extraordinary mobility for hydrogen within the lattice. Given the extraordinary mobility, it is inconceivable that two hydrogen nuclei would occupy the same trapping point and fuse at a loading ratio of less than 6. What trapping the octahedral points does do is limit the uncertainty of the position of the hydrogen nuclei. All of the lattice structures that support the transmutation of elements have this trapping capability. In atomic, molecular, quantum, and optical physics, as well as in quantum chemistry, molecular Hamiltonian is the name of the operator representing the energy of the electrons and nuclei in a molecule, to be taken as the trapped hydrogen nuclei and the lattice elements in a unit cell, or the first Brillouin zone of the matrix running the reaction. This Hermitian operator and the associated Schrödinger equation play a central role in computing properties of molecules and aggregates of molecules, such as conductivity, optical, and magnetic properties, and reactivity. By quantizing the classical energy in Hamiltonian form, one obtains a molecular Hamiltonian operator that is often referred to as the Coulomb Hamiltonian. This Hamiltonian is the sum of the 5 terms depicted on this slide. That's the starting point, but it is used to describe systems in equilibrium. Specifically, the 4th and 5th entries in the description of the molecular Hamiltonian are the description of a system that is undisturbed. When the molecular system is moved away from equilibrium, nonlinear effects begin to dominate. In general, the evaluation of the Hamiltonian results in another function. The function of the ECR hypothesis includes terms not previously included in a Hamiltonian, because ECR addresses a system far from equilibrium. When the superposition of phonons compresses the lattice containing a hydrogen ion, one must add 2 additional terms. I submit that within the solution space of this expanded Hamiltonian, there are absolute values that achieve 782 keV and even 3 MeV, as demonstrated by deuterium-palladium systems. The non-bonded energy, or Lennard-Jones potential term added to the Hamiltonian describing ECR refers specifically to atoms that are not bonded to each other, as indicated in the picture on the left. This energy accounts for repulsion, van der Waals attraction, and electrostatic interactions. Van der Waals attraction occurs at short range and rapidly dies off as the interacting atoms move apart. This is represented by the black line portion of the graph on the right side. Repulsion occurs when the distance between interacting atoms becomes even slightly less than the sum of their contact radii. The hydrogen in the lattice is not bonded and actually causes some deformation of the lattice on entry, indicating that it is forced entry into the blue-green portion of the graph on the right. It is the 1 over r to the 12th effect, driven by the interaction of multiple phonons, that is a large driver of the electron capture events, and actually acts as a multiplier to the Heisenberg confinement energy covered in the next slide. Again, this is the first additional term to the Hamiltonian responsible for driving electron capture reactions. Brillouin Energy was able to obtain a Technology Assistance Package, or TAP, from Pacific Northwest National Lab. In discussions with their scientists, I told them that if they simulated confinement of a proton to a small enough volume with electrons around it, the Heisenberg uncertainty principle alone would provide the energy necessary for the proton to capture an electron by conversion of energy to mass. The conversion of energy to mass would result in the formation of an extremely low-energy neutron. I was told that it was not possible for a proton to capture an electron by providing energy. I asked, can you test that in a simulation for the TAP? The answer was yes, and a few weeks later they came back and said, you're right. This graph is the summation of the simulation results. These results further confirm the Brillouin energy ECR hypothesis and further validate our work. As I mentioned earlier about the fields that I drew on to come up with the electron capture reaction hypothesis, there are usually multiple ways to describe the same thing and several related things that have the same solutions, just using different variable names. I think Peter Hagelstein's lossy spin boson model is a more complete mathematical description of the same thing. Although Peter is agitating for direct nuclear interactions instead of weak nuclear interactions, it is an excellent model that results in similar effects.
When the system energy, or molecular Hamiltonian, achieves or exceeds 782 keV, the energy necessary to make up the mass difference between a proton plus an electron and the mass of a neutron is present. At this point, the hydrogen nucleus undergoes an electron capture event as a natural energy reduction mechanism. This highly endothermic reaction, in combination with the dispersion of the phonons that cause the increase, results in a cold to ultra-cold neutron. Neutrons are attracted to each other, but the attraction is not strong enough to be bound. At energy levels of a few millieV, 38 millieV is roughly 70 degrees Fahrenheit or 21 Celsius. At this energy level, the Brownian motion will shake the multi-neutron systems apart. However, a deuteron that has just converted up to 3 MeV of energy to mass has an extremely low energy level, low enough that the neutrons remain together long enough to interact with another hydrogen nucleus moving through or into the lattice location occupied by the newly formed neutron or neutron cluster. This is similar to concepts used in astrophysics and referred to as the S and R processes, which build heavier elements inside of stars through the accumulation of neutrons and beta decay. In electron capture reactions, ultra-cold neutrons interact with another hydrogen nucleus,
moving through the lattice, resulting in 4H. Part of the problem for established physics is that so much of their information is based on big science accelerator experiments. This led to a policy at the National Nuclear Data Center, NNDC, that defines the ground state of a nucleus as the lowest energy level at which it has been observed. The first 3 links that you are likely to run across at the NNDC in relation to 4-hydrogen indicate that it undergoes a 100% neutron ejection decay path, even at what they have arbitrarily defined as the ground state. Another document states the mass of 4-hydrogen as being greater than the mass of tritium plus a neutron. This was referred to as an unbound nucleus. What that means is they have called the ground state the lowest energy level that a nucleus has been observed at. For 4H, that was the immediate aftermath of a 7 million electron volt collision. That's roughly 10 times hotter than the core of the Sun, and has nothing to do with reactions taking place inside of the metallic lattice. A paper called A=4, available at Duke, shows the calculated half-life of hydrogen-4 when produced below 3 MeV is either 30 milliseconds or 10 minutes, depending on the spin polarity of the system. Besides the bullet points, Brillouin Energy has assembled a fantastic multidiscipline team. We have mechanical, chemical, software, aeronautical, and electrical engineers. All of our team members have some understanding of one or more of the other disciplines. Even our CEO has won awards in multidiscipline engineering. He also has a great deal of business experience, including knowledge and understanding of deal flow. We also have a great fundraiser and CFO, David Fershine, who screens all of the contacts coming in through the website, which should be getting an update later in 2015. We are actually starting to talk with some companies about development contracts to complete the transition to a technology. If we can close one of these deals, we expect 2016 to see the completion of a true technology and the emergence of the first commercial use of our technology as pictured in the background of this slide. In summary, the electron capture reaction, ECR hypothesis, provides not only an explanation of the reaction, but points to multiple ways to make industrially useful devices by controlling the underlying physics. Ultimately, we believe this technology will power a significant portion of the post-carbon economy. with clean, green, affordable, controllable energy that is available and reliable anywhere, anytime. Brillouin Energy. The best way to predict the future is to invent it.